So you probably have been hearing these words in the last year when I think ChatGPT just came in and everybody's like, wow, what's happening? The story is that this is not a new idea. It just is bigger, as usual. And when certain things go beyond a certain threshold, it looks like magic. So this is kind of that story. This is not a research talk, just to be clear. I'm trying to give you a historical perspective, introduce you what's going on, what has gone on in the last 30, 40 years, demystify some of the internals. I'm not going to talk about prompting or anything like that. Every time I go to read some things like, hey, prompt engineer this, prompt engineer that, totally bogus things. So I'm going to give you so that next time you read something, you have some more context and you can appreciate and or find the holes in or whatever. Right? So what is natural language processing? I start usually my talks with sort of a one slide giving you that this is engineering. It's a subfield of computer science, although it's a subfield of computer science. There is no such thing as theoretical NLP. It has to be implemented. You can't wave saying, hey, we can do it. Okay, so that's one thing. And there are three legs onto this. Enabling human-computer communication, okay? So dictating, for instance, email messages, which I routinely do on an iPhone, okay? Enabling or enriching human-human communication. That's things like real-time speech-text translation. Comes in very handy in Tokyo, where you have no idea. Summarization, given a document, what's the TLDR, okay? And more importantly, for inclusivity, dealing with speech-to-text, sign language to speech and text, so those people can communicate. And there are these things called, actually developed by someone from CMU, the Seeing AI apps. This is for visually impaired people. There's an iPhone sitting, and it's reading into your ear what it is seeing on the. And if it's somebody you know, it says John is in front of you, just say hi or whatever. It's just whispering in your ear. So it's a lot of good stuff. And then we have a bunch of things that require human language faculty, which we know how to do, but we can't do it at scale. Okay, these are things like spelling and grammar correction. Okay, especially the latter is quite useful now if anybody is using Grammarly or something like that. Document search, that's what Google is doing that. Question answering. Think of it as, for us academics, TA in a box, which actually we are currently using in a system called Didero, developed by my colleague Umut at main campus, where students and or faculty says, question has an answer, the student has a question, you say, generate me an answer. 2 seconds later, you have some answer. Whether you trust that or not is a different issue, but it seems to be working at least. I have some of my students here, and they said, yeah, it occasionally is helpful. And you can just extrapolate from what you're seeing today to see that this is going to be an extremely important application. Real-time fact-checking, verification, given all the crap that's going on. It's a very hard problem. I did a lecture on this in the course I'm teaching, both in Pittsburgh here. I got depressed. And depressed because we're not even anywhere close. This is like for what Giselle is doing, but for actual texts, you have a new law or regulation coming up. How do we know it has no contradictions or incompatibility with anything prior? How do you fix it? So there is some reasoning you need to do. This is like program verification, but with human languages. In our dystopian future, you probably will have something like this, where you have the judge and the jury and the executioner in the box, and will read your case and pass a judgment. Okay? There are now workshops starting to take place covering that area. This is beyond finding case files in the US legal system. Okay.
Language is, for all practical purposes, effortless for us. We don't think about it. I'm speaking, you're hearing. I'm not speaking very slowly to help you understand and so on. It's very natural for us, right? We learn the mother tongue effortlessly. If you're exposed to multiple, takes a little bit longer, but not twice as long. Okay? Well, I know that because I have a grandson who's now doing that. Yet, we have no idea what these concepts are. We use it randomly, haphazardly, but if I ask what is the meaning, there's no formal description that we can give, neither for understanding, although we use them, right? We understand how certain things work, but they're not terribly operationally useful because it's not observable. We can't really undo it or understand what the components are doing and so on. Okay? Now, the worst thing is, and this is the problem, is everything in language is ambiguous and everything hinges on context, period. The rest is just a transformation from one form to the other. Okay? People are extremely good, machines not so. They use experience, whatever that is, common sense, whatever that is. Okay? In fact, we know what it is, but we can't define it. Okay? Or extra-linguistic signals like the Italians doing this and that. Okay? So what is context? Everything we quote-unquote know, this could be formal, laws of calculus. This could be linguistic, grammar of our language, and so on. Native speakers know what's in their language, what is not in their language, easily. Cultural things, what we do, this is how we do it here. We do it differently in some other place. Okay, and then common sense, again, this is the situation. I'm in a room, I'm talking to a bunch of people. That's my local context. And it's 4 p.m. past 4 p.m. and my mental notes, I know where I am. What I am seeing, what I have heard recently as part of some discourse, okay? All of these go into creating some data structure, quote unquote, but for lack of a better word, that helps me solve this ambiguity, okay? So, here's a sentence. And this, through some intuition that has nothing to do with linguistics, is describing that situation. It is that larger box. Okay? Worse is this one, where grammatically I have the same sentence, except one word has a different semantics now, and it is describing the following situation. How do we know that? Well, we know it, and we have no clue. Okay? By the way, this information is not in the linguistic signal. Although you could probably reason not fitting means that something is large, something is small. You can probably do that. But we do this effortlessly, is the point. Recent observation, this is about maybe 60 years old, over 60 years old. You shall know a word by the company Keeps, James Firth, a British linguist. He basically said, we can use context to infer semantics. So I'm using now a word here, which I don't see any Turks in the room, so they probably wouldn't know what it is. Okay? A bottle of gilaburu is on the table. Okay, suddenly you know it's a bottle, should be something for drinking because it's on the table, or the table is not terribly important at that time. Everybody likes it. Maybe it's like Coke, right? Makes you feel refreshed. It's good for your health. By the end of the fourth sentence, you have a pretty good idea what kind of an animal you're dealing with. Okay? I was force-fed this when I was small. I hate the taste. Okay? But it's very local. It's extremely, quote-unquote, good for you, I guess. So context gives me the meaning. I didn't tell you anything about that word. I just gave you how it is written is irrelevant, actually. Okay? So you kind of infer something based on your prior information you had. Okay? So how can I build up on this? Here's something called a keyword in context representation. This is ever since 50s, 60s. Lexicographers look at word usage and characterize them by context and see if they correspond to genuinely distinct meanings, so that they figure out how many entries a given head word in a dictionary has. Okay? So this is for the word chicken. This is all the, there are probably more. I never printed that. So the goal is, hey, here are all the different ways the chicken is used. Can I say something about the meaning? So people in the last 10 years came up with some computational procedure that takes all of that, runs it through this concoction, and gets you the meaning representation for chicken. You have no idea what those numbers are. The only thing you know is it's a vector of 1,000 elements. You have no idea what each of those things, what dimension they're capturing and so on. And it's kind of impossible to figure out. Okay, so this is a chicken and eggs problem, obviously, because I need to know the meanings of the other words, because one word impacts this and they all impact. So it's a sort of, at the end, you get everything together. It's a kind of iterative procedure, not just like. Anyway, so that led to the first breakthrough, about 2013-ish, called word embeddings. Okay? You get a dictionary, and dictionary says able is that, book is that, and zygote is that. Okay? So that's good. At least now, instead of a dictionary, we have another dictionary whose content we have no clue, but seem to be useful. Okay? So people did initially some visualization on these things, and they said, the vector difference, at least visible in the two-dimensional space between king and queen, uncle and aunt, they seem to be pointing in the same direction. Maybe that vector indicates maleness or femaleness. Okay? Some sort. Or people did things like, hey, if king is to kings, let me use this one, then and then I can go to a queen, and then if I take this vector and add the queen, I get queens. People said, wow, that's cool. That thing is coming up with some interesting stuff. Okay? We actually play with this in the course here as the first homework, you guys, right? So they try to find that kind of analogical reasoning tasks. Other things, brothers and nieces, nephews and nieces, brothers and sisters, aunts and aunts, kings and queens, emperors and empresses, and so on. Okay? Not exactly, but good enough that there is something going on there for further. Okay? Loose ends. I went through that fast, and you probably didn't notice it at the time. But you see this? That's a different chicken. Okay? So we are conflating different senses and such. Language is notorious for this kind of stuff. Okay? And figuring out which of these one is using in a given context has been notoriously hard to crack. And people got depressed, and it's still not cracked fully. The problem is called word sense disambiguation. Which sense of the word am I using here? Okay? So NLP today is basically given a bunch of text. Let's assume we're just doing text processing now. Translate them to embedding somehow. Very simple. Use that table. Do all your magic on those representations. And then finally, when you have something to output, there is a way so that we can go to the human side of things and present the result. Okay? Classical language models. Now, so that's just sort of a snapshot. Okay? Classical language models are what people thought were language models, say, starting at 1988 or so. Okay? And it was mainly statistical. Nothing like these grammars and so on. People, especially linguists, tried very hard to defend grammar, but they were totally ignored because it couldn't account for anything that the engineers wanted to use for. So this is nothing but something that gives me a probability for a given sentence. The model being a set of parameters theta, which is learned somehow. I'm going to briefly mention one slide with that. But it assigns that. Okay? It's a model of plausibility, not necessarily of grammaticality. It will be nice, but I'm not going to insist too much because there will be sentences where humans are not necessarily terribly grammatical. Intuition? Well, something like this, a sentence likely to be used in normal daily real-world settings, you want that probability to be higher than something like that, which is highly unlikely to be used, but otherwise it's a nice grammatical sentence versus something like that, which is total word salad, which a version of which Chomsky used that syntax and semantics are separate things and so on. Okay? So let's see how good your model is. So this is a quiz. Okay, so what is your next word here? You don't know, because, right? But if I give you that, suddenly your search space collapses. And there are, 4 or 5 uses of prime at that stage. Now I say this. Oops. Now you know you're referring to a person probably, or some entity, okay, who's prime or not at the given point in time. Okay. And you say prime of his life, and so on, right? And then you say the prime. I'm taking answers. About it? Huh? Prime number. Okay, I actually did that because of time reasons, but the other one is minister. The prime minister gave what prime ministers give. Huh? Speech. What else? Money. Speech. Okay? Nah. How about now? Something that starts with a vowel. And so it could be an argument, it could be an ultimatum, right? Whatever. So that's a local phonetic pattern because of the way English works. Okay, how about this one? The prime. You're missing one major prime. Huh? Prime? Reason. No. Rib. A prime rib. Okay, prime rib was delicious. or, oops, you would say, model will say, I can't deal with this. Okay? Why is that? Okay? So this was 2013 when I was getting ready for my lecture. I went to Google. Google at the time would give you how many times a search result appeared in its database. So the prime was that many times, the prime of his life, 14 million times. Apparently, women don't have as many primes as the men, so it's a bit less. Prime Minister, 121 million times. Is that right? Yeah, it could be. It's like a third of it. Right? Prime Minister gave Prime Minister gave N, so number of N's is one sixth or whatever of the A's. Okay, prime number, Christos, prime rib, pretty common. Prime rib was delicious, outstanding. Okay, so we don't see that. When we don't see it, we don't have a representation, and we say, now it could be blue, by the way, like rotten stuff, but highly unlikely. So this kind of data, billions and billions and billions of words, give you enough to compute some statistical abstractions, okay? Now, what's in the language model? Well, we have words which we don't really care how they are written, because it's just random choice of things. A, P, P, L, E has nothing to do with the fruit or the company, the way it's written, okay? So we represent words with their identity, meaning this is the first word in the dictionary, this is the 1,000th word in the dictionary, this is the millionth word in the dictionary. You have a finite dictionary for English at least, okay? The only context we're capturing is positional. We only know what comes before, in fact, close by, okay? The underlying simple mathematical framework is not efficiently able to look at much larger context. So you can approximate this probability using chain rule as like, what's the probability that the sentence starts with the? What is the probability that the is followed by prime? What is the probability that the prime is followed by rib? Etc., until what's the probability that the sentence ends after was delicious? Okay, those we can compute. Okay, what are those parameters? Well, let's assume I'm looking at two previous words as my context, which is kind of a standard size called trigram model. I have three things in, two of them condition the third one. Okay, so what's the probability of rib given the prime? How many times did I see this? Divide by how many times did I see that? That's simple as that. Okay? Now, a lot of technical issues underneath, because remember, we're doing engineering. Okay? So remember, in the previous slide, I was multiplying a bunch of numbers. Those numbers are very small numbers. You multiply 10 of them, you end up underflow. We cannot represent that, so people said, we're not doing that. Let's go to the log space, and now instead of multiplying, we're adding, and then the logs are reasonable. Okay? What happens if you don't see a word? The probability will be 0. Well, that's not good. I'm multiplying them, so I can't have that. So there's something called smoothing, the kind of the Robin Hood approach. We take some probabilities from the seen words and then distribute them to the unseen words in a very small amount. Okay? Not worth here. Where do we use a language model? So I hope this works. And use that in speech recognition. And I'm going to now play a little clip. And I want to learn how to recognize speech. Okay? You heard that one? But I actually spoke that one. Okay, so you were primed to interpret that one. Okay? So acoustics is extremely ambiguous at the signal processing level. It's the latter set of constraints of word orders and frequencies and all the other things that constrain it so that you put the right. Okay? Contextual spelling correction. Let me give you a couple of examples. We're leaving in 5 minuets. You all know you're not. Okay? But you're leaving in 5 minutes. Now, the spelling corrector will not flag this. It's a legit word. The grammar checker will probably flag that. We listen to 5 minuets, that's perfectly fine. We listen to 5 minutes, no. We listen for 5 minutes, sure. Okay? So these are now words that are contextually misspelled, not necessarily misspelled by themselves. Okay? Machine translation, big part of the systems built since 1992 onwards, called statistical machine translation, not the ones currently being used. We're using these kind of languages. Word segmentation. Japanese, Chinese, they are written like this. You have to figure out where the words are. I finished German, I'm now doing Duolingo Japanese. Man, that's builds up character. Okay? It's weird. But it's written one chunk, and then you have to figure out where the words are. Now Japanese speakers do it without any effort. Okay? Arabic speakers, they see this and they immediately figure out what the unwritten vowels are. Because Arabic, the modern standard Arabic at least, the ones used in certain stages, once a person grows up with a certain language skill set, they don't write all these extra stuff, which probably the reason is that slows down writing, so you don't want to write it, but it's ambiguous, and then you have to figure out the actual sounds if you want to do text-to-speech, for instance. Okay? Japanese can't pronounce every word the way we pronounce it, so they have to retrofit it into their syllable structure. So sukurachi is scratch. Okay, now, if you're translating from Japanese, you see that token. What's the most likely English word? But could it be sugar? Right? I don't know. But it's anyway. Why language models should not work? Linguists say the man on the sidewalk, without pausing to look at what was happening down the street and quite oblivious to the situation that was about to befall him, confidently strides. Okay? The verb is pretty far away from the base operation for the subject. Okay? That is outside any reasonable context. Okay? Sure, but is that really a reason? So Michael Collins, in his 1990-something thesis, said they are quite rare. Okay? In the mid-90s, people at UPenn built this database of sentence annotations, and Mike Collins said 74% of the syntactic dependencies are with an adjacent word, so it's not far away, and 95% are only 5%, five words away. So this whole thing is a big miss, long distance. Anyway, so what do they know? They sort of learn common or rare patterns, some kind of local syntax, what comes after N versus what comes after A. Things like you eat apples, but you don't eat books, kind of. Some punctuation and spelling, and they have no idea about sentence structure, absolutely nothing. Yeah, they see patterns, but they can't really abstract. Okay? They have no idea about meaning or semantic relations. They have no idea about the world. Okay? So, this is another word that goes along with language models, generative models and so on. The only thing it says is you can generate, in a probabilistic manner, sequence of words from this model. It captures some distribution of what comes after what. So in the class, I use this thing, dart throwing thought experiment. Okay? So I have words W1, W prime, W double prime. I have a dart. Of course, it's supposed to be round, but hard to deal with the drawing of that. So, okay, I have something like that. Okay? Each of these is given those, there's one dart board for every unique pair of words. The size of that part of the board is what's the probability of word 1 after those two? What's the probability of word 2? Okay? So you can estimate these from the data you have. And now you throw a dart. Dart lands there. Okay? And you say, aha, I'm going to choose this guy. That's it. Now, ideally or intuitively, when it falls, the chances that the dart will fall on one of those rectangles is kind of proportional to the size of that rectangle. Okay? It's very narrow, may not. So you keep on doing that, and you get crap like this. Okay? Where you will see these equations were presented in both cases, which looks like amazing. And then, I don't know, something like matching zone weighted graphs. And then it goes off the deep end here. Okay? Now, if you do this with 4 or 5, you can get better ones, but you're limited by the narrowness of the context. That just doesn't help you. Okay, so they're based on large amounts of text with discrete tokens. We're talking about billions and billions of words, whatever you put in. They capture only very short and very superficial and positional context, nothing more. They don't capture semantics. Okay? So where do we go from here? Okay, so what's different now with instead of discrete identity-based representations like W1, word 2, word 3, whatever the vocabulary size is, we have what we call continuous high-dimensional representation for each word. That's those vectors with numbers in, okay, that we get through some procedure, which I showed with this distillation thing in the beginning. Okay? That was roughly 2013 or so. I mean, the idea behind those things came and basically rocked the field. Very large context, so hundreds to thousands to hundreds of thousands of tokens. And now there is talk, I mean, I got a paper I have to read, is infinite contexts, meaning as large as needed. Okay? Neural networks and deep learning. Okay? And in that, basically 2018 or so, Google came up with a certain generic architecture, which everybody is using now. Nobody has started playing with it. Maybe in 5 years, it's going to change to a different flavor, but this is now the workhorse. Okay? Most important conceptual breakthrough is something called an attention, which is a simple idea, but has changed the nature of the. And it basically tries to answer the question, hey, I got this context, which ones do I really care about? Not everything's equally relevant for me. There are some syntactic sugar items there, like the articles and words that are not terribly semantically useful. Okay? So, you don't have any information about what potentially comes next, right? If I give you a little bit more, still probably, but there are things openable, at least, whatever they are. Okay? What kind of things students open? Books, laptops, right? But not necessarily like doors, because they don't have a door for each student. there is some implication there that this is one-on-one, right? And I give you some extra stuff, but still that doesn't give you any information. As the professor started the clock, the students opened their exams. Highly likely. So what gave it away? Okay, I mean, professor, pretty far away, clock, okay. The reasons professors start clocks is some timed event that's kind of in the situation, okay. I don't have any other choice for a name. I pick up Khaled. We spoke with Professor Khaled Haras in CS. 5 sentences later, we say, he looked into that, said professor. Well, what goes in here? I mean, there are 8 or 9 professors in CS, if that is any help, but clearly it should be a name, we know that one. Hard to tell who. Okay, so how do we copy information from the context so that those two are kind of semantically the same thing? So this extremely influential paper came out, 2017, mind you. It's like 120,000 citations. Okay? Intuition, 1. Relations are not just positional, but or with nearby constituents. There are all kinds of linguistic relations that we don't even know the cardinality of. Not everything in the context is equally relevant. How do we zoom in to the relevant part? That's the a priori, we don't even know what possible relations. Every language encodes different kinds of relations. I mean, English is different for Arabic and French and so on, right? So one is agreement, like keys and are somehow related. Chicken crossed the road because it wanted to get. So who's chicken? Well, it's this guy. So there's co-reference. This is kind of, I have the word pond, I have the word bank. Clearly, it's not commercial bank. Okay? Because there are other things that kind of point to bank as the bank of a river. Okay? Word sense resolution. Situation as the final week, as the professor raised the board, the students open their exams and so on. All those things describe a certain situation in our mental model. And then we kind of think this one is not a board, like a skating board, but rather some other board, like the white blackboard or whatever, because of the context. Okay? So what is attention? How do we know what is relevant? Well, we don't. But we can learn them from the data. Okay? As long as we have a mechanism for learning it, we will learn what those are. We don't even know all possible relations. How can I be sure I'm looking for a certain? Well, learn them from the data. Whatever makes your life easier or whatever makes your accuracy better. Okay, we can learn that. Okay, so we spoke with Professor Khaled Haras in CS, He looked into that, he said. Okay, so I have to figure out who he is. So this token says, I am looking for a noun describing a male person. Okay, male person is part of the representation of he. Somewhere in the representation for he, there is this maleness. It says, I'm looking for someone. Anyone out there? The tokens from Professor Khaled and Haras would say, I'm a noun describing a professor. I'm a noun describing a person. So you get these responses back. Okay? So you're querying, you're getting responses back. And now you can say, if these match, meaning there's some similarity between he and these guys, then you copy that information that you get from those guys into the information representing he. So he at that stage looks more like Khaled than, say, myself. Okay? Because I'm not mentioned in the context. Okay, so that's kind of what's happening. this is done by basically everyone. So these are different words. Let's say we looked into that is somewhere here, and let's say he is here, and everyone that's coming is to the left. Okay? So information from the previous ones are flowing to the right to help the information output for subsequent elements. Okay? That's because of the left to right or beginning to end constraint of the language. So we have an item of interest here. We compare it to a collection of previous relevant items. Okay? And then we compute some representation that combines the responses of the previous guys. Okay? It's like the only technical slide I have. These are vectors. Dot product is large if these things are non-zero in roughly the same places. So the score function will be high for representations that give you me a high dot product. Okay? So this is technically, for CS people, is random access, looking into the past, content addressable memory. So the system is remembering in the context the values of certain things. You don't know what they are. You're just broadcasting, asking them, and they're saying, this is who I am. You're taking them, and then you're weighing them. Okay, so the weighing happens something like this. Ignore the math, but it basically takes each pair and assigns a score, and then the output is a weighted sum of the inputs coming before. Okay, I don't know what this is, but I know how to compute that. Okay, I will leave it at that. The actual technical details are a little bit different, more general, but it's a way to find a weighted sum of previous values, hoping that whatever you're looking for has some relation to you in some dimension. Okay? There can be different types of attention, not just one. Well, add more attention units. It's just computation anyway. Okay? Each attention unit is randomly initialized. So when they are exposed to the same data, they go in different ways and become sensitive to different relationships that appear in the data. There's nothing humans or the people do to fine-tune that. They say, randomly initialize some internal set of parameters, then run the 1 trillion words through the system, see what happens. Okay, again, this is slightly different, but I have multiple heads. These are going to attention heads, ignore the mathematical notation. Okay, I combine them in some way and then make some additional mappings and get some outputs. That's pretty much it. Okay? What is learned in the process are these parameters. These are weight matrices for different parts of the math. Okay? But we don't do anything. All we do is, you did something wrong here, and it will go and fix the weights through the backpropagation procedure, which I'm going to skip. Okay? So all these things come together into a unit like this. All that attention stuff happens here. There is some additional stuff to prevent certain things going haywire. So there are copies of the data made that bypasses anything coming through attention and so on. And at the end, we get... Now, this is a huge network, by the way. Billions and millions of weights. Okay? Three flavors I'm going to look at briefly. Two, autoregressive models, fancy name for everything depends on something coming back before it, that's all. GPT-4, okay. Masked language models, this is actually the first important model that came in 2018. And encoder decoder models, which we'll look at. Okay, now, I have those blocks. I piggyback them large number of them on top of each other. One output of one goes to the input of the other one. So 12 layers for GPT-3, but 4 years old. 96 layers for GPT-3 large, 120 layers for GPT-4, 1.8 trillion weights to tweak inside that network. Okay. At the end, you get some representation for the word. It goes through some other massaging. You get the probability. Probabilities are saying something like, hey, this is possible words you can generate here. Here are the corresponding probabilities I computed for you. You can pick from them. If you pick the largest one, that's one approach. You can pick randomly. It's another approach, like I did. Okay. There are many other ways to sample from these. Sampling is the formal name for picking the right word. So all these things like write me in the style of Shakespeare. So you get all these thou shalt, thou hast, whatever. That's playing with the generation choices. Okay? So here's your prefix text. You give it through, everything goes through here. You generate, you get a bunch of words, and then you pick whatever the word has the highest probability or whatever your choice is. Okay. Then you take that and you plug it here to get the next word. So you're extending the context. That's pretty much what's happening, almost like the thought experiment, but the much larger scale. Okay, so maximum context is fixed but large, and now it's growing larger and larger. How do you train these things? You have trillions and trillions of text. You give the text to it. You run through that. You get probabilities, and you know what you're supposed to generate, right? The next word goes up there. So everything is shifted by one this way. So you know what your output is, so there's no annotation needed. If you don't generate that, you get a slap in the wrist, the red thing, okay, that goes through the system. So the first you do forward pass, go this direction. Are the outputs what are expected? Yes, fine. If not, you have to go back and tweak everything, okay? And then go to the next sentence, and then you start over again. I mean, these things takes weeks to months to run with huge GPU systems. One thing I should say that the old GPU is just there, because all this computation can be done as a bunch of vector matrix multiplication, which GPUs are ideally suited for. Okay, the fact that it's called a graphical processing unit is kind of a misnomer. Originally, they were developed to do graphics processing on laptops. Anyway, so some NLP tasks for word prediction. Sentiment analysis, you probably know what kind of this is. I take my context sentence as the sentiment of the sentence I like Jackie Chan is, and I find the value of positive in that context using some API. Gives me a number. I get the number for the second one, compare. Whichever is larger, that's my. So question answering, find the word that maximizes the probability, saying, hey, Q colon, who wrote the book, blah, 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 A colon. There's nothing special about Q and A. I'm just giving it for human consumption. And you find the word that you sample from that, and you find the word with the highest probability. Assuming you get Charles, then you can just plug the Charles back in and complete his name. Okay? I have maybe another 5-6 minutes worth of stuff. So in this model, this is what we call a causal model. The information flows from left to right. Okay? The Google people said, why is that so? Why can't we look at everything? Because there's more information. I'm going to be doing potentially interesting things. Okay, so what they defined was something called the bidirectional model, BERT, and several other variants of it. What it does is, it takes an input like this. It either masks or corrupts some of the inputs. So you're not seeing this. This is known as close task in psychology or some field like that. No, okay, C-L-O-Z-E, close task. So the goal is, given this, try to figure out what these are and fix that one. Okay, so you're supposed to get long there, tanks there, the other ones are fine, and you want to get do there. If you don't get, you get a slap on the wrist, you go and fix the weights, and so that next time you see that. Now, these are randomly inserted at every stage, but 10%, 15% of these tokens are corrupted. Okay, so that's one thing it learns to do. The other one is, I have two sentences in a row. Is the second sentence something reasonable that can follow the first sentence, called next sentence prediction. So you can take your texts, take every two sentences, put one after the other. They're all reasonable things to follow. And then you just put garbage sentences in the second one. Those are negative examples, so you don't, or you get the kind of, this is not a next sentence for me result. And there's one token at the beginning of this thing, which basically gives you 0 or 1. 0 if it is not a valid next sentence, 1 if it is. Okay? This part is basically encoding some semantic relation between the two sentences, whatever it picks to encode. Okay, remember this? Right. The last layer outputs in the BERT thing are actually representation of these words, but specialized to the context they appear in. So is this a plural tank or a verb tank, which have different senses? Okay? So words like this in these contexts will have a different representation versus the plural tank. So there will be a noun or a verb depending on the use, although in the dictionary we have one entry which kind of composes both of them together. Okay? So the chicken entry has the two things combined together. We're undoing that. So this is the token DIE. This is a multilingual model, so it has German in it and English on it and so on. Okay? So it learns different clusters without it being told anything. Okay? So this is a single person dying situations, kind of on this side. Okay? Versus multiple people dying on this side. Okay? And then we have Las Vegas dies, okay, on that side. And then on this here we have German uses. One is a nominative and the other one is accusative. The subject of a preposition. Okay? So this is nice. At least it takes us somewhere towards the... couple of things we do at the end. We have BERT. Google has trained it using its massive resources. It gives that out free. Then we can build something on top of it, a neural network, to do something useful. Okay? We call that fine-tuning. We have our own data. So in the class, we do something called the clickbait detection. Okay? Clickbait is a real text, and this is text meant to take you to the rabbit hole. Okay? Couple final closing notes. Does attention work? So these people published a paper in National Academy of Sciences. So these are heads, attention heads, the 10th head in the 8th layer. Remember that big multi-layer thing? Okay, so direct objects attend to their verbs. Okay, so funds and plug. Okay? Plans and discuss plans. Okay? So those weights are kind of showing up. Prepositions attend to their objects, so off, in, and to. Okay, active, in, trading, off, bonds, and so on. Okay, so this is searching for a needle in a haystack. And it's not clear if there's anything, but we don't know if this is actually what's happening in the way we process language. Some more examples. So, computationally very expensive, time and money. It's quadratic. I have to compare everything to everything else. There are linear approximations, but you get lesser accuracy, which nobody wants to get because then somebody beats you. Okay. Final comments. Okay, so I guess there are some stars aligning here. The field is going transformative stage, and I'm kind of at the end of my, not immediately, but we make jokes amongst ourselves like it's the right time. Is it just LLMs or machine learning? Is there something else going on? I don't know. There's a lot of philosophy behind this. Books cannot keep up with what's being done. I mean, literally, we can't keep up with the syllabi. I mean, we changed everything last semester for the Pittsburgh course from scratch, 25 lectures, mostly LLMs. And then we have to change a little bit because of things that happened in the fall and early this year. It's just crazy. Anything prior to 2018 is considered classical in an affectionate sense. Okay? And then you ask people, so you don't parse sentences? Which means, do we figure out what object is, what verb is? People say, why? Okay? People spend 50 years honing their parsing skills. And suddenly it's like down the tubes. Okay? I mean, Newtonian mechanics has some use. It's like 400 years old, although the model is whatever, the current quantum mechanics model. Here, anything before 2018, nobody remembers. Nobody cares is the worst part. So, I don't know. There are many opportunities, though. I mean, you're following this automatic generation of videos from verbal prompts. What was it, Fora? Is it called Fora? Anybody seen that? Type something, show me something, somebody walking through Times Square, and then you get a video, right? Text, image, speech, all kinds of things. There are joint trainings of these things. You show a picture, you show a video, you show the text, and it learns what happens where, and so on. It's not necessarily something doable in a university setting, given the computational things needed. Many problems. Data. Is that too much data or not? Like all the written stuff since prehistory, is that something we need to use or not? Clearly, we're not doing the learning part right, in my opinion. Humans don't always learn from data. They basically get a slap on the head and they say, aha, that's how it is done. Okay, so it was like instructions. This is how you do it. And then I'm kind of noticing that now that I have a grandchild. You tell him to do something and immediately you don't have to even demonstrate. You say, but learns to do it. Environmental effects, it's a big deal. You're using a lot of electricity, all the carbon and all that stuff. There are systems that track unused sources. So most of the electricity in California is actually coming from northern Quebec. At night, nobody has anything on, so they're selling at bargain prices. Okay? Bias. You're reflecting what's in the data, and then data has all kinds of nasty stuff. Okay. Reasoning without kind of these multi-step hand-holding kind of thing is still not there. Okay. Hallucination probably will get better. But as you're generating, if you make one little error somewhere, it will change your direction in a rather weird way, and then everything else after that, just like black hole. The models themselves are frozen in some time. Like, they finish doing something in 2022, that's it. What happens afterwards, right? So what people said was, hey, we're going to use Google to get some useful documents, put those documents as the prompt, and then generate. So you have the original model built into the weights, you have the relevant documents making up your prompt, however large, and then you generate, so you take both the old model and the new thing into account and so on. Thanks and acknowledgements. Yeah. Thank you. Any questions? Not that I can answer all, but Mohammed, why did I know you would ask a question?
So you stressed a lot on the idea that context is the most critical thing, and you had that statement from 1957. And then it took actually the field all the way, even word embeddings that you spoke about with techniques like word-to-vec or glove. They came 2012 all the way till 2016, 17. They are feature representations. They are not contextual representations.
Embeddings capture the context.
But the true contextualized embeddings came...
No. Those are different. Contextualized embeddings is different than embeddings.
Sure. Even if we count from 2012, optimistically, it took the field from, 30, 40, 50 years, by the way, to just actually recognize, we know that the context matters, and now we can apply it.
Oh, no, they knew that context matters way before. So I have let me show you one slide.
Why haven't they done anything?
Oh, they did. All these simple, like the spelling correction problems, they were using context right and left. Okay, just lest you think this all happened in this age. No, it's not. I have a slide here. This one. This is the quality of machine translation systems. This is about maybe 5-6 years old, so it probably is a little bit different, English, Spanish, and so on. The blue ones are using classical language models. Okay? The biggest jump that people got was not with that one. The neural models after 2014, 15, 16, the RNNs and then now transformer-based models, they're the cream on the top or cherry on the top. Okay? So the biggest advances actually is based on, or if you stop and didn't do any of the fancy language models, you'll be at the boundary of the blue ones. Okay? And they were 5 grams at most. Nothing more. Okay? Yes.
So maybe a quick one first and then a longer one. So the quick one is you said that every word is mapped to a vector, and what the component of every vector is, we don't know. But saying correctly that for the classical models, we know what that number is the probability that
we know exactly
this is going to appear, but only when the neural networks came up, that's when we lost track of what's happening. Okay, good. Another longer one. So you said at the very beginning that there's no theoretical NLP. There's only... I want to understand that statement more. So meaning that doesn't matter what you do, in your head, you need to apply it, then it becomes important. But isn't that like an opportunity for theoretical aspects?
Of course. But those are all the way into towards the eventual deployed application. That's what people care about. Okay, there's a separate area which is kind of related called computational linguistics. It's kind of doing some linguistic processing using computational means, extracting all kinds of level of information that may or may not help downstream tasks. But at the end of the day, what matters is how good your system is doing on some benchmark, at least among the industry people. There are benchmarks, like 50 different tasks, question answering, sentiment analysis, summarization, and so on. People build a model and then look at the numbers, and it's a chase. Everybody's chasing everybody else.
All right, last one. What's your guess about us eventually understanding what those numbers are? What is your guess about us eventually understanding what the numbers in the components are? What is the meaning of these numbers? Anywhere?
And nobody is looking at it because there are 11 trillion numbers that give some interpretation on those numbers. So it's just, every input vector that you're given is touching everything with those 11 billion or trillion things and create you something. Nobody has the time to probe that. People attempted that. It's just not humanly possible.